So, which interpretation of quantum mechanics do you think works best and why?
Works best is a difficult one because all the ones that are serious work. And that's part of the fun with the interpretations thing, is that you've got several things which all describe the phenomena we've got. So to some extent it's a bit of personal taste which one you choose. Personally, I've always been led towards the many worlds interpretation because I agree with Everett, who came up with the many worlds interpretation, that you should somehow let the theory drive the interpretation and not put your interpretation on top of try to fit it into the facts. And to me, quantum mechanics naturally gives you many worlds, which we're quite happy with at the microscopic level, but we're a bit more unhappy with for the world around us, but I don't really see the distinction. So to me, that's always seemed the most logical. If you accept that that's the quantum mechanics is the theory that we're happy with, that to me seems the simplest.
Sure. Yeah. Why do you think on the microscopic level that it's apparent that there are many worlds?
So if you get a very small quantum system, an atom, an electron, anything like that, we often write this as a superposition, just a sum of different outcomes, different possible outcomes. Right, so it might be, for an electron, it might be something like a superposition of being in the spin-up state or the spin-down state. And we're quite happy to write the so-called wave function of that object as a superposition of two outcomes. And if those outcomes were to stop interfering with one another, then they would go off on their everyday, they would go off and they would not interfere with each other, they wouldn't know about each other. They'd be independent things. Now, at the macroscopic level, you can show using decoherence and stuff, that a superposition naturally decoheres into non-overlapping wave packets. Right, so these are worlds, if you like. They're macroscopic wave functions that don't interfere with each other. And you would have no idea about the others because they become dynamically independent. So you could describe this whole room around us with a wave function, and it would be part of a larger superposition. There'd be many other rooms with their own wave functions. And the universe as a whole would be a superposition of these, but they don't interfere with each other. And this is a natural consequence of decoherence, which is just quantum mechanics in a different environment. So we naturally get, from the principle of superposition, which is the fundamental point of quantum mechanics, we naturally get non-interacting, macroscopic, classical-looking worlds that don't know about each other. So,
okay.
Yeah.
On the principle of superposition, how should we understand something like the thought experiment of Schrödinger's cat? Because it doesn't seem like it's possible for there to be such a state where the cat is neither dead nor alive. It must surely be in one or the other, and it's just that we don't know about it. So how would we say?
So that's exactly what I'm saying about the interpretation being forced upon the system. Right? We've got a classical intuition that cats are alive or dead, because we never see anything otherwise. But I would imagine you don't have the same prejudice about an electron being in a spin-up or a spin-down state. In homeworks and stuff, you're quite happy to write a wave function which is a superposition of the up and down state. Now, in the Schrödinger's cat's experiment, so what was lovely about Schrödinger's cat, it was actually invented by Einstein, not Schrödinger, it was in a letter to him, is that he just made the point that there really is no difference between an electron being in a spin-up, spin-down state or a cat. At no point is there like a sharp cutoff where things stop behaving like electrons and they start behaving like cats. Right? And actually Schrödinger didn't like that. I mean, he used this as a way of saying, well, this is absurd, but but I agree, I completely agree that there is no difference. So with the Schrödinger's cat experiment, you have two outcomes of something like an unstable atom, decayed or undecayed. And we're quite happy in first year undergraduate to write a wave function which is a superposition of decayed plus undecayed. And we have no problems with that. We're told that's how quantum systems work, and most of us accept that. We don't assume that there has to be decayed or undecayed. Right? I mean, that would be our classical intuition. It has to be one or the other. We just don't know which one it is. And what the Schrödinger's cat thing is very good for is it shows that you can couple this microscopic system through a process called amplification to macroscopic systems, whereby this superposition is passed on to higher level things. Right? So if you assume that that quantum mechanics is a theory of everything, we're all made up of atoms and stuff. Those are quantum mechanical systems. There's no reason why they shouldn't also behave according to quantum mechanics. So we have the decayed and undecayed, which will couple through interaction to the detector. So the detector gets put into a superposition of detected or undetected. And this can get passed up, and the mathematics is very easy on this. It's just unitarity. It gets passed up and up and up and up, to the point where you might have some macroscopic thing, a cat, which either dies or doesn't die as a result of this decay or undecay. And at no point is it obvious which one you should start treating like a cat and which one you should... So there are two ways of thinking about this. Either that the cat is really in a superposition, contrary to your assumptions, or maybe the atom is never in a superposition, right? And that perhaps... So those are the two extremes. At one end, we've got the many worlds interpretation, saying that the wave function of the cat really is a superposition of the two. And you never see a superposition because of this decoherence thing. So they dynamically decouple, and the two cats never know about each other. So they're quite happy. They think that cats are either alive or dead. On the other side of the scale, we can push it right back down and say the atom was never in a superposition. It was always in one state or the other. And this is the idea of the hidden variables, which is that the quantum superposition is actually a bit of a mirage. It's just due to our ignorance we write it that way, but really we should be writing it like we write cats, alive or dead. And then you get various intermediate interpretations which say, no, it ends somewhere in between the two. Right? Stuff stops behaving like an atom at some point and starts behaving like a cat. And then they get into all sorts of trouble saying where that happens. Right, so that's where you get in more sort of the Copenhagen interpretations.
Okay. With respect to the hidden variable theorem, do you think it will ever be possible to find the hidden variables and make quantum mechanics deterministic?
Yeah, well, with hidden variables, it's important to remember that they're only hidden until you do a measurement. Once you've done a measurement, the system collapses into a definite state and reveals what state it was actually in. It was decayed or undecayed. You're just ignorant of it until you do it. So hidden variables is actually kind of a bad name for them. No, I don't believe that we'll find a hidden variable because I think the premise of the endeavour is false. Because by looking for hidden variables, you're refusing to accept what nature is telling us, which is that the world behaves in a very indefinite way in terms of superpositions. You're trying to force the cat, alive, not alive, mentality onto atoms. And people are happy with that because we are macroscopic objects. You know, they like that, and they tried doing this because also all of the mechanics, all of the machinery of physics for hundreds of years was built around that basic assumption of reality, that things have a definite existence and they have a definite position and they have definite properties. Right? So it would be quite cheap, theoretically, to be able to just transpose all of that down onto the phenomenon we don't understand. But they've tried doing this for over 100 years, and it has failed in all but one occasion, which would be the Bohmian pilot wave theory. But even that is not a typical hidden variable theory. That itself has plenty of strange implications. But in terms of the local hidden variables, which is what most people think about, which is trying to describe the world in terms of classical existence, they've tried this, and I'm sorry, it's failed at every stage. There really is almost no prospect of doing that anymore. And I think it comes down to the fact that the approach is incorrect.
Okay. With respect to interpreting things as many worlds or Copenhagen, how would you respond to the entanglement problem with the EPR paradox, that things seem to move faster than the speed of light if you separate two particles and they don't know the other's spin? It seems that if you measure one right after the other one, it will always be the random opposite of the first one. So how does that not violate relativity?
Yeah. So again, that really comes to the heart of how you view the world according to your interpretation. If you were a local hidden variable person, you wouldn't have any problem with this whatsoever. That's the attraction of the local hidden variables, right? Because if two things go off, they carry with them information, right? If they're in a definite state, they were in that state when they were separated. There's no mystery, right? So it's just like you can do it. You could do it classically, right? If you have two things that separate and they agree here that one is one way and one is the other, and then they go off, and then you do a measurement on this one, and it turns out that the other one is the opposite, there's no mystery there. There's only a mystery if you think that they were never in that definite state from the beginning, which is what standard quantum mechanics says. So it says so standard Copenhagen quantum mechanics, I mean, there is no real such thing as the Copenhagen interpretation. There's lots of different things that people think. Says that nothing is not in any particular state until you do a measurement. So the act of doing the measurement has collapsed it, and that brings forth the problem of how did that one over there know that you did a measurement over here? Yeah. But the way to think about this is that relativity says that, so locality in relativity says that no signal can be traced from one point to another if they're space-like separated. Right, but quantum mechanics, it still respects that, so there is no faster than light signaling, but you have non-local physical states. So in classical mechanics you have local states, particles, and you have local communication, nothing faster than the speed of light. The difference in quantum mechanics is you can have non-local states. You can have states that are smeared out over a large area, and this is exactly what happens in the UPR thing. So you prejudice the discussion when you start talking about two particles. Because two entangled particles, they don't have separate wave functions. They have one wave function. Right? They behave as one object. You can't separate them. You can't disentangle them in any particular... It's meaningless to talk about two particles once they are entangled. They really have a common existence. And so doing something to one particle over here, you really are doing something to the whole thing. Yeah, so you're not getting communication between states faster than light, but you are acting on a non-local state. Right, and this is how it gets around the special relativity thing. However, of course, because you're not actually sending a signal, you're just acting on a non-local state. You can't send any communication faster than light. So you might be able to say that something is happening faster than light. You know, there is an action which is doing something across a large space-like separated area, but you can't use that to send any useful signal. And there's theorems to that effect. So you can't send classical information faster than the speed of light. You might be able to say you can send quantum information, but we can't use that for communication because we're used to using classical information for communication. In terms of many worlds, there's no problem here whatsoever, because as far as the many worlds is concerned, the two particles go off in different directions. They share a common wave function. When you do a measurement, one of them, a bit of this wave function becomes entangled with a much larger system. This starts breaking down the entanglement between the two states, and the various overlapping wave functions go apart. So in the many worlds, they have a really, what I think, neat way around this is that special relativity is conserved, but by getting rid of a more fundamental approach, which is something called counterfactual definiteness. So we're used to the fact that if one thing happens and it's mutually exclusive to another, then the other thing didn't happen. Right? And that's a sort of a more basic thing than sending communication. But that jettisons that. It says everything happens. So it saves special relativity by making events non-exclusive, by saying everything happens. Okay. Which is, some people might think is a bit of an extreme way of doing it, but then, you know, all the alternatives are not particularly good either. So.
You said earlier that local hidden variable theory had been disproved in all cases.
Yeah, there's a few very tiny loopholes, but I don't think anybody credibly really...
Okay. Could you explain how Bell's inequality rules out local hidden variable theory?
Yeah, so in a local hidden variable theory, we think about objects, like, you know, my hand or whatever, as having properties assigned to them. Right? So an object will have an energy, it will have a position, it will have a velocity, and these are labels that you can just tack onto the object. And as it goes about its life, these labels might change, or they might stay the same. But they are always well defined. Now, in local hidden variable things, they try to do the same thing, but to a quantum object. Now, in quantum mechanics, as you know, the only thing you can ever measure, these properties, are things called eigenvalues. They're special values. So the fundamental assumption of a local hidden variable theorem is that the properties of a particle are its eigenvalues at all times. Right, so its spin has two eigenvalues, spin up, spin down. It is always either spin up or spin down, and it carries that with it, that information with it, and it doesn't change. Now what Bell showed is that if you make that simple assumption, if you entangle a few of these things together, but then on top of that you add the assumption that that when you write down the wave function, you actually say they are in eigenstates. They have to be in eigenstates all the time because they're classical-like states. And with that extra little assumption, he was able to show that there should be an inequality that's satisfied. Right? So it's a very, very basic, this is why it's such a powerful theorem, because it's a very, very basic assumption. You know, it really goes to the heart of what a local hidden variable theorem is. And then you can test that inequality. And it has been tested over, well, since about, was it 1984, again and again and again, and it's been shown that that inequality is violated by reality. And it's violated, you can also calculate it in quantum mechanics, and it's violated in quantum mechanics, but the important thing is it's violated in reality when you do an experiment. Yeah, so that whole, and there's been even more stringent theorems beyond Bell's theorem on not just local hidden variable theorems, but this very idea of local realism, that objects possess definite values at all time. It's clear that they don't. Now in quantum mechanics is a bit more, I mean in Copenhagen interpretation it's a bit more difficult to say what is really going on, because Copenhagen interpretation is completely blind to what is really going on. They don't care about what is really going on. They just care about the outcomes of experiments repeated many, many times. So if you want to actually understand what's really going on, you have to have a more sort of liberal approach to what is allowed at the microscopic level. Many worlds says, I don't have a problem with things being in indefinite states. They don't need to have definite properties at all times. If you have a non-local hidden variable theorem like Bohmian theory, that means they have definite values, but those definite values can change according to what's happening to the wave function. So you have to loosen your prejudices about reality to start describing what is really going on. Because the most naive thing, the local hidden variable thing that we'd all be very happy with, and we wouldn't have to worry about philosophy or anything like that, because life would be very simple, does not work. That's been shown, does not work.
Okay. You mentioned that Bohmian theory is the one case where it has worked. Could you just explain how this works and why it can describe the observations that we've seen in experiments?
Yeah, so the pilot wave theory, due to de Broglie, and then brought back again by David Bohm in the 1950s, is a remarkable theory. And it's a realistic theory, unlike the Copenhagen interpretation. It really is what we call an ontological theory. It really is telling you what is happening in reality. And this is something we're told we're not allowed to think about in quantum mechanics. But David Bohm has showed it, and it's very, very simple. So we're used to just having a wave function, and what he says is there is a wave function, but there's also a particle. Right? So it's not wave-particle duality, it's a wave and a particle. So we think of the normal wave function, but on top of that we've got an extra component, which is the particle. And this tells us what the definite state is. And this particle goes about, and its motion is dictated by the wave function. So there's a reciprocal sort of relationship there. So the whole quantum state is in a definite state at all times. Now normal quantum mechanics is just missing the particle. Right? So that's why we don't understand what's happening in each thing. We can only calculate averages. In the Bohmian theory, we get an extra piece of information, which is the particle, and that tells us. So the best example of this is in the double slit experiment. Right, so in the normal double slit experiment, we send a quantum state through that is behaving like a wave. It's got a wave function. It interferes with itself when it goes through the two slits, and we get this nice interference pattern. But in any one event, we just see one little flash on the screen. Right, so it behaves like a wave when it's going through the stuff, but it arrives as a particle. So trying to understand why that possibly happens has led a lot of people into a lot of confusion. Yeah, because we see one particle, but if we do it many, many times, we see the interference pattern building up. Now, why on earth would that possibly happen? Well, Bohm's got a very simple answer to that. There's the wave, it goes through, it interferes with itself. This wave guides the particle. Right? So the particle can't move in any direction it wants. Right? It's guided by the wave. And the particle, simply guided by the wave, goes through one of the slits. It doesn't go through both or anything like this, it just goes through one of the slits, and it goes along a path dictated by this interference pattern, and eventually hits the screen and causes a flash. Right? And of course, if you do that many times, the particles will go along all sorts of paths guided by the wave. And over time, you will build up the interference pattern. But there's no paradox. The particle is at all points in a particular place. It goes through one slit or another, and it arrives at the screen, just as you would expect. Right? So in many ways, it's really liberating, the pilot wave theory, because it removes a lot of confusion. Why it was never accepted, I think, has probably got more to do with sociology than physics. It's a fascinating piece of history and sociology why it was not accepted. But to my mind, it's extremely powerful. It's extremely. When I'm thinking about quantum mechanics, I often think about what does it mean in the pilot wave theory first, because it's much easier to make sense of it in the pilot wave theory. And it's not without other applications as well. I mean, like I say, it's a realistic theory. Right? It is telling you what is actually happening in reality. Whereas the Copenhagen interpretation says that the wave function is not a real thing. It doesn't describe anything real. The only thing that's real is once you do a measurement and you get a result. Right? So in Copenhagen, the only real things are the empirical data when you do a measurement and you build up the results by Born's rule. But what if you want to describe something like the universe? Right? If you want to describe the universe as a whole, well, you can't do a measurement on it. You're part of the universe. Right? There's nothing to collapse the wave function. Right? So the Copenhagen interpretation can't tell you anything about the universe. And you maybe think, okay, that's fine, because the universe is a classical thing. But what about the early universe? When we're talking about when a lot of cosmologists want to describe the very early universe where things start behaving quantum mechanically. But you can't do that with normal quantum mechanics because there's no experiment there. There's no experimenter to collapse the wave function. So Copenhagen interpretation tells you absolutely nothing about a situation like that because it's not a theory of things. It's a theory of knowledge. And if there's no one there to know it, then it's not a thing. Whereas pilot wave can quite easily. You know, the universe will have a definite configuration, and you can calculate it. And a lot of cosmologists are beginning to use the pilot wave theory for exactly that, because they need a tool to be able to do quantum mechanical calculations that don't require the collapse of the wave function.
So could we use the pilot wave theory to predict what's going to happen? Could we get to a point where we understand how it's guiding the particle or what path it might take?
Yeah, so the pilot wave theory is a hidden variable theory. And the hidden variable is the position of the particle. Right, so this is something, so you don't know the position of the particle a priori. Right? You find out when it hits the screen. Then the hidden variable is revealed, but you don't know what it is to begin with. So if you knew that to begin with, then you could predict with certainty where it's going to end up. So if you had a wave function for the universe, there will also be so it's not a particle as such when you're describing the universe, but a point in configuration space that tells you what is the actual configuration of the universe. And that actual configuration will evolve deterministically, driven by the wave function. Right? And you would be able to say exactly what will happen to the universe in a completely deterministic way. But you need to know where that is to begin with. And we don't know what that is. But what we do know is that in a quantum system, particles are distributed according to the Born rule, which is the square of the wave function. So if that is so you can still do statistical things, and you reproduce the results of quantum mechanics exactly. But the pilot wave theory gives you so much more than quantum mechanics, because you don't just calculate averages. In quantum mechanics, you only calculate averages, or eigenvalues, but averages basically. And as you know, when you do an average, you lose a lot of information. And statisticians use that on purpose, because a lot of your information is useless, and they want to just get down to the bit that survives the average. But you can do something much more in quantum mechanics with pilot wave theory. You can actually understand what is the system doing exactly, but in a real world thing, you'll never know what it is until you do the experiment. So yeah, the pilot wave theory can give you a lot more, but it's a question of how useful is this information. For philosophers, it's extremely useful because they're able to say that the universe is in a definite state at all times. And that's radically different from other proponents of, say, Copenhagen, saying the universe is a completely indefinite state until you do a measurement and then it collapses. And what about all the other bits of the universe? How do they know it's collapsed as well? So it cuts through a lot of the philosophical rubbish. So it's got huge utility in that respect. There is also the possibility that the pilot wave theory could be tested as different from standard quantum mechanics. So when the particles are distributed according to the Born rule, the square of the wave function, then the results are exactly equal to quantum mechanics on average. But it's possible to distribute the particles slightly differently if you want to. I mean, it's not possible to do that in an everyday experiment, but it's conceivable that they could be distributed differently. And if they were distributed differently, then they would produce results which would be different from quantum mechanics. And it's not inconceivable in the early universe, they may have been distributed differently. So they has this remarkable properties that if something is what we call out of quantum equilibrium, which is when they're not distributed by the Born rule, just by normal time evolution, they very quickly become distributed that way. So today we're used to quantum mechanics with its Born rule, and it tells us that these particles are distributed like this. But in the past they could have been different, and it's just now we've relaxed into equilibrium. Right? So where now we get confused because we've got quantum mechanics on this side and the pilot wave, and they're indistinguishable. But it might have been in the past they were actually distinguishable. So that would show up quite starkly. So some people do this. Look at early universe stuff like the CMB and stuff like that. Look for signs that you could actually find non-equilibrium dynamics in the early universe. And what's even more remarkable is that if you're away from equilibrium, special relativity doesn't hold either. So the pilot wave theory is a non-local theory, but it respects, just like quantum mechanics, because it gives the same results, it respects special relativity on average. But if that average is not calculated exactly the same way because the particles are slightly differently distributed, that special relativity is also violated. So it opens up the prospect of the very early universe having different, not just different results, but the actual framework being different to what we're used to today and violating locality. So it opens up quite an interesting window on of possibilities on the early universe. Usually when we're talking about the early universe, we still assume Lorentz invariance, and we still assume quantum mechanics being correct. But it might be, it's not just new fields and new particles and stuff in the early universe, it might be that the actual framework that we use could be different. And the pilot wave theory gives you an opportunity to explore that, which I think is fascinating. Whether you think it's correct or not, I think it's incredible to be able to expand your framework using an interpretation. That's why I don't actually personally adhere to the pilot wave theory, but I think it's a wonderful invention and deserves to be explored a lot further.